In Module 7c, we're going to look at the theory behind long short-term memory networks, LSTM, for time series analysis. So this presentation is going to talk about, or is going to review, what is the feed-forward neural network architecture and how can this be extended to recurrent neural network. And we're going to see why can recurrent networks solve our problem with time series problem, and how does it justify using LSTMs. In terms of LSTM, we're going to look at what is the general architecture, and more specifically, it involves gates, and we're going to see how each of the gates involved in LSTM works. Finally, we're going to look at a complete example where we compare the performance of what we saw in module 7a and b, state space models and BDLM, compare with LSTM. Okay, when each of the methods shine, what can they do? How are they complementary? Okay, and that is an additional module in a category of supervised learning. Why is LSTM categorized as supervised learning, whereas state space model were unsupervised learning? Remember, in state space model, we were trying to separate a time series into several subcomponents, and we're especially interested in the interpretation of those subcomponents. And here, we never provide label output to decide what should have been those subcomponents. They were learned on their own by the state space model. On the other end, here with LSTM, we can consider it as a supervised algorithm. Why? Because here we're really interested in the input-output relationship. Okay, we try to learn the relationship between the previous history, the current covariate that could explain our time series, and its output, where we provide labels for the time series data. All of these categories are kind of blurred, so it can be part of it belongs to one to the other, but generally we could consider that LSTM belongs to supervised learning. Okay, so let's review what we already see in Module 5, the feed-forward neural network representation. So here's an example of a X input node, Y output node, feed-forward neural net. So the nodes on the left, represented in pink, are the variable on my input layer. Here my A's for each of my hidden layers are my activation units. So here I have L hidden layer, each containing the same number A activation units. For each activation units, I have a hidden unit. And remember, the difference between a hidden units and an activation units, it's a nonlinear transformation. So each hidden unit, before going to the subsequent layer, is passed through a nonlinear activation function, whether it's ReLU, sigmoid, or tanh, for instance. At the output, in purple here, I have my output layer, which represent where I have as many nodes as I have observation that I want to fit. And finally, each of the arrows here represent parameters that I'll have, either a weight or a bias, that allow us to go from a hidden layer to a subsequent one. So here, instead of using that full expanded notation in this module, we're going to rely on this compact notation where each node represents a vector either of input variables, activation units or hidden units, or output units. Okay, and all those feed-forward connections here are going to be represented by a full arrow, in this case also represented by theta, the vector of parameter that consists in all the arrows represented here. Okay, so let's look at an example in the context of what do we want to do with neural network in time series. So let's imagine we want to model the behavior of a dam such as this one with respect to time. So what we could do, we could try to put in relation, say, the displacement of the dam represented here by a caliper. So you can see this is a small caliper I've put here, with respect to the temperature, ambient air temperature, and for instance, the water level behind the dam. Okay, if we would like to try to model this in a regression setup in terms of our inputs are the temperature and water level, and the output is the displacement, I wouldn't take into account the time history analysis of this time series. Okay, so I would discard part of the information. So what we want to do here is not only to look at the snapshot at time t, what is going on, we want to also factor in the time history analysis in order to improve our predictions. Okay, and the simplest way to do this with neural network, or at least the simplest way to represent this, is through recurrent neural networks. So it means neural networks that have connection through time. So this is the same representation of a simple feed-forward neural network as we saw earlier. Instead of being horizontal, it's now vertical, okay? We have our output here, we have our input, and we have two hidden layers. If we want to transform this into a RNN, recurrent neural network, the only thing we have to do is to look at consecutive time steps, and instead of having only as input, for instance, my first hidden layer, instead of having as input only my input layer, it's going to have my input layer as well as the hidden units on the previous time step. Same thing, my second hidden layer at time t is going to have as input the hidden units from the previous layer as well as the hidden units from the second layer at the previous time t. Okay, and we can unfold this through time over all the time steps for our time series. Okay, but the issue with RNN is that sometimes we're interested in long-term dependency. What is the displacement today as a function of maybe the temperature 6 days or 60 days ago, because there could be some thermal inertia in a structure as large as a dam. So in such a case, the problem with RNN is associated with vanishing gradient. What does it mean? Is if we're trying, when we're going to try to learn the parameter of our neural net, to look at what is the derivative of the output ZO at time t with respect to the input at time t minus n, where n is even moderately large. In that case, it causes a problem because that derivative will tend to 0. So we're losing the relationship with respect to from the output to the input if the sequence is too long. So that makes RNN extremely difficult to be trained. And the solution to go around this is LSTM, long short-term memory network. So here we have the same feed-forward neural network we had before. That can be easily extended if we look at it recursively over time in RNN. Here we're going to see how we can transform this RNN into a LSTM. So we keep our input, we keep our output, but we replace what we had here as fully connected layer by, in the simplest case, a single LSTM cell. So the LSTM cell has 3 inputs, 2 outputs. Okay, the 3 inputs are first the same X as before. The input variable we had, the same thing as we had on our previous RNN. But it also has these 2 inputs, which are the hidden state from the previous time step and see the cell state from the previous time step. And now what are the output? The output are going to be the new updated cell state and the new updated hidden state. And then we see that we have a connection. So our prediction from our neural network is going to be obtained by putting some connection between our updated hidden state to our output layer in the same way as we have on the output layer of a fully connected neural network. And here we don't only have something at time t, we have again that history. And that cell state, which is like acting as our memory, is carried on through time. Same thing for our hidden state. And that allows us to go around the difficulties associated with vanishing gradient when we're trying to have long-term dependency. Why? Because we don't need to carry out the long-term dependency over the previous time step, because now the dependency will be stored in our cell state. Okay? So the key behind the LSTM cell is the memory that we have by using CT or cell state. So here we have a C component vector, which all the members in my cell state could be real number, okay? And the key is that this is gonna carry from the past what is the relevant information I need to consider now in order to make good and relevant predictions. So if we look more closely into what we have here, what's inside that LSTM cell? We saw there were 3 inputs, two outputs. So the previous cell state, the previous hidden state, and the input vector. Okay, this is in the input side. On the output side, we have the updated cell state, the updated memory of our network, and some hidden states. The hidden states can be really interpreted in the same way as the hidden state we had in feedforward neural network. So within that LSTM cells, what we have several gates. Okay, we're going to break that down and we're going to look at them one by one. Typically, when we represent LSTM cells, we often have that output connection where we simply replicate our hidden state to really distinguish between the part that is carried forward and is going to be passed to the subsequent time step, and distinguish it from the one that is going to be passed upwards towards either the output of our network or to even maybe another LSTM cell. Okay, because we can stack multiple LSTM cell on top of each other. But just keep in mind that this here is simply a duplicate of what we have here, nothing special. So the LSTM gate, what did they allow us to do? Everything we have here. The forget gate, the first one we're going to see here, allow us to erase from our cell state, from our memory, what is the irrelevant past information, okay, that we already had at time t-1. Then the input gate and the candidate value cell will allow us to write in our cell state what is the new relevant information we want to store in our memory, okay, in our cell state CT. And then finally, we can, using the new updated cell state, use a subset of this memory and focus our attention on a subset of these cell state in order to make predictions that can depend not only on the immediate past, but on event that happened a long time behind in the past. Okay, we're going to look at the first gate, the forget gate. So you can see here we have the forget gate denoted by F. Okay, so before looking at the forget gate, let's keep in mind a little reminder. What is my cell state? So the cell state at time t-1 is a C component vector that describes what did I remember from the past. So you need initially to initialize what is going to be the size of my cell state, and inside my cell state, theoretically, it could be anything. So any real number in C dimension. Okay, this is going to be my long-term memory. Then what I want to do with my forget gate is to tell me from my past history of my cell state, which one do I want to erase? Which one do I want to forget? And to do this, I need to obtain numbers from my forget individual values between 0 and 1. So those that are going to be to 1 are going to be kept. Those that are going to be to 0, I'm going to be completely erased. And here it's not either 0 or 1. It can be anything between 0 and 1. Okay, but the size of the cell state and the output of the forget gate are going to be exactly the same size, because at the end, the forget gate and the previous cell state are going to be multiplied, so that whenever F is 0, that value is going to be erased, okay, from my past memory. And again, keep in mind, it's not either 0 or 1 for my forget gate, it's anything between 0 and 1. And so that 0 here is just an example. So how do we obtain that forget gate? We're going to have the information from the previous hidden state at time t-1 concatenated with xt, which are going to be my input vector. That could contain, like in my previous example, my water level and my temperature, say for instance. I'm going to concatenate those two, multiply this by a weight matrix, okay, so that the output of this multiplication plus this is going to be the same size as my cell state. Okay, this is exactly how we transit from one hidden layer to the output, the other hidden layer. Then we're going to add, so W, keep in mind, it's a matrix of weight. B, it's a vector of bias parameters that are going to shift my response. And then the output of all of this operation is going to be put, or is going to transform into a sigmoid function. So the sigmoid function, remember, this is the blue curve we have here. It's a curve that takes inputs in the real numbers, and outputs are going to be between 0 and 1. Okay, and this is what we want. We want the forget gate to then tell me which one I keep by putting them at 0, which one I can erase by putting them at 0. And we can be somewhere in between as well. Then the next gate, so what we saw before was the forget gate, the first one here, where we say which one from the past do we want to erase or forget. Now we're going to look at the input and candidate gate. How do we enter new information in our cell state? So then we're going to take into account the previous information for the hidden state as well as the input, and we're going to say which of the cell state, which the variable of the cell state do I want to modify, and what value do I want to store in? These values are going to be in my candidate values cell. So my candidate value cell here, C tilde, contain what is the new information I potentially want to store in my cell state. And by definition, this is going to have the exact same dimension as my cell state I had before. And now in my candidate value state, I'm going to have the range of values could be between -1 and +1. Here, my input gate, what is it going to say is which one of my cell state do I want to modify with my candidate value I have here. So if I want to modify, it means it's going to be all the values in my input gates are going to have first the same dimensionality as my cell state, and they are going to be between 0 and 1. So 0, I don't want to modify this value. 1, I want to modify it by the full extent of my candidate value here. Again, it's not 0 or 1, it's anything between 0 and 1. Then when we're going to multiply the input gate with the candidate values, I'm going to say those for I, which are 0, are not going to be used or not going to be updated. Those with something that is high, for instance, 1s, are going to be updated. So here I put 0, but this is just as an example, okay? So how do we compute that input gate? It's exactly in the same way as we computed the forget gate, except that we have now separate parameters. So we have a separate weight matrix, a separate bias vector, okay? But the structure is exactly the same. That weight matrix is going to multiply the concatenation of our previous hidden state and input vector. We're going to add the bias. We transform all of this into a sigmoid function. And the output is between 0 and 1. This is our vector of input gates. Then our candidate values are obtained by doing something similar. We have, again, a weight matrix that is different from the forget gate or the input gate. We have the concatenation of our hidden state and input vector, and we have a vector of bias. And this now, instead of being transformed into the sigmoid, which output something in between 0 and 1, now it's output in a tan H. And as you can see here in red, the tan H has an output between -1 and 1, and again takes input from -infinity to +infinity. Okay, so it means that at the end, my candidate cell values, my candidate cell state is going to be in the range, each value is going to be in the range -1 to 1. So then my updated cell state that I can have here and that I'm going to carry forward in time is obtained by a part where I forget previous information and a part where I write new information. So if I multiply element by element, the values for my computed forget gate with my previous cell state, I'm going to remove some information from the past, and I'm going to add the product element by element of my input gate and my CT. Here there's a little typo, it's not T-1, it's CT. So my current candidate value state. Okay, so the product element-wise of these two, the addition is going to replace here my new cell state. Okay, now that I have my updated cell state, I want to use that updated cell state in order to obtain my new vector of hidden state that is duplicated on top and on the bottom here. Okay, so to do this, I need my output gate. So my output gate is going to kind of focus my attention on only a subset of that memory, okay? Because in that memory cell state, okay, I store things that I'll need now, but I also store things that I may need in the future, but I don't need now. Okay, so that output gate, what is it going to do? Is that it's going to focus our attention on just a subset of the variable in the memory. Okay, so again, to do this, the output state is going to have the same dimensionality as my cell state, and the values in the output for the output gate is going to be between 0 and 1. So when I'm going to multiply both element by element, we're going to keep to the full value the one for which the output gate is 1. We're going to reduce to 0 those which are 0. And again, we cannot necessarily have to be between, we can be between 0 and 1. It's not only either 0 or 1. Okay, so now if I want to look at what is going to be my output gate, it's going to be very similar to what we had with the input gate and for the forget gate, which is a weight matrix, which is dedicated for the output gate times the concatenation of my previous hidden state and input vector plus a vector of bias. All of this transform into a sigmoid function so that my output gate is between 0 and 1. So finally, my output hidden state, what is it going to be? The product element by element of my output gate vector and the tanh transformation of my cell state at time t. Okay, so what is it going to do? So O can be between 0 and 1. So it's going to focus on attention on simply a subset of the cell state, those that are relevant. So the part of the memory that are relevant to predict the current quantity at time t. Okay. So at the end, what we're going to do, so the output layer is going to be connected to the hidden vector we just compute here in a fully connected fashion as we have on the output layer of a traditional feedforward neural network. Okay, not only we can do this, but we can also, if we want, have multiple LSTM stacked on top of each other. So in that case, instead of having our output layer connected to the hidden state of my first LSTM cell, I'm going to connect the hidden state of my first LSTM cell into the input of my second LSTM cell. Then the output of the hidden states of my second LSTM cells are then going to connect to my output layer. Okay, and we can step, if we want, a great number of layers of LSTM network in that way. So let's look at an example where we want to look at the performance of LSTMs, but also compare how do they work with the state space model and BDLM methods we saw in module 7a and b. So we're going to look at here the monitoring of a dam. So what you see here is a view from the top of a dam here. So we have upstream view, we have downstream. This is a topographic map which represents the contour of a valley where we've put that arch concrete dam. And here we have two sensors, CB2 and CB3, that we want to model. So you can see here an elevation view of the dam. So this is the rock that the bedrock you can see here. So this is the kind of the shape of the valley that they block with a concrete arch dam. So the CB3 sensor is here. We're going to measure the displacement, so the radial displacement of the dam at this point on the bottom. And the CB2 is the radial displacement on top of the dam, so the crest. And you can see here, if we look at the side view, you can see this is the kind of cross section of the dam where we model here, or we have measured the displacement at the bottom and at the crest of the dam. So the two data to measure the displacement are obtained from inverse pendulum, which are a typical device to measure displacement of dam. So we can see in blue, this is the crest displacement, and in yellow, this is the displacement for the bottom of the dam. So on average here, we have data from 2000 till 2013. These represent the displacement in millimeters, and this is a non-uniform time step length. We have roughly 1.4 data points per week, okay, over a 13 years period. We have also, as explanatory variable that are going to enter in our covariates, we have the reservoir level, what is the water level behind the dam, and we have also the temperature. So we have two temperatures that are recorded on this dam. What you see here are the yearly cycle of the air temperature. So if we look quickly just at the relationship between the sensor CB2, the crest, and the water level, we see that we don't have a clear relationship between these two. Same for CB3 and water level. We see that there's a nonlinear dependency, but it's not a clear one. It's not easy. It's not just a one-to-one relationship. Same thing if we look at CB2 or CB3 and the temperature, TA, we see that it's a big blob. It's not easy to extract directly from a regression analysis what is going to be the dependency between our sensor values and those explanatory variables. Okay, and that's why we want to do a time series analysis. So in this case, what we want to do is to compare the predictions from an LSTM network with those obtained with BDLM. So here the total data set we have is from 2000 to 2013. So for that whole duration, we have the temperature and the water level. And what we're going to do is that we're going to try to predict simply the water level, assuming that we have as available the temperature. No, we're going to predict the displacement, whereas we assume we have always as available the temperature and water level. So we're going to use the duration from 2000 till 2009 as our training set for both approach. In order to tune the hyperparameter associated with each approach, we're gonna use a 1-year validation set from 2009 to 2010. And finally, our test set to compare the method are gonna be from 2010 till 2013, okay? So for the LSTM architecture, we use specificities. It's LSTM with teacher forcing. What does it mean? In this case, we have a single LSTM cell, which take as input the water level and the temperature, but as well as the previous observed value. Okay, in this case, that's called teacher forcing. It allows to improve the prediction by forcing the network of getting closer to your predicted value. Okay, but otherwise, this is the same architecture as we had before. One specificity that we have here is that we don't train this neural network using the gradient backpropagation as we've seen in the module 5 and 6. Here we train it with a method we've developed called TGI, Tractable Approximate Gaussian Inference. What does it allow to do? It allows us to do Bayesian inference in neural network. So in this case, we can handle two sources of uncertainty. The parameter uncertainty. This is what we do with our Bayesian analysis. With TGI, we can quantify the posterior for all the weights in our LSTM network. Also, the second source of uncertainty is going to be the prediction errors that goes between the output of our neural net and the observation. There can be a prediction error associated with either measurement uncertainty or prediction uncertainty, so the incapacity of our neural net to exactly predict the DAM's response. So now if we compare the predictions we have obtained with BDLM on top here and LSTM on the bottom, this is for sensor CB2, the crest of the DAM, you can see that both are fairly close to the data that is represented in red. Whereas in black, it's the expected value of our prediction. And in green, this is the 1 sigma confidence region, either for BDLM on top, LSTM on the bottom. If we want to measure quantitatively what is the performance of each method, we can look at the log likelihood for that test set, which is minus 63.9 for BDLM, minus 65.9 for LSTM. So here we have a slight edge for BDLM. If we look at the sensor CB3, which is the bottom of the DAM, you can see again, red is the actual data, black is the expected value that is predicted, and the green band is the confidence region around that prediction. We see that again, both methods are fairly close from the data. Here we see we're a little less good, so we might have again a little edge for BDLM, minus 12.1, minus 30.2. So BDLM again has a slightly higher, or in this case, a much higher log likelihood. Okay, so how can we compare the pros and cons of each approach? So both show in general a good accuracy. Okay, this is not where we really discriminate both approach. Both can handle uncertainty. Okay, there's a asterisk here. Why? Because in the case of LSTM, plain LSTM trained with backprop won't be able to do this. Okay, if you couple it, however, with tractable approximate Gaussian inference, you're going to be able to do it in this case. So BDLM is compatible with non-stationary data. So as we saw in module 7b, when you have like change in regime, you can adapt to this in BDLM. In LSTM, it's not the case. You have to have stationary data. In the case of BDLM, the component, the hidden state you obtain, as we saw in module 7b, are interpretable. So whether it's a local level, a periodic component, a dependency on the water level temperature, we can interpret and make physical sense of what's going on. With LSTM, we can't. We're really good at predicting, but there's very little we can interpret out of it. Finally, this is where the main difference is. BDLM require a manual setup. Okay, so it takes some time and it takes some experience to select the proper component and build your model. And on the other end, with LSTM, it's a black box setup. Okay, you just need to provide what are going to be the configuration of your network, what are going to be the input, and you can analyze and crunch the data. You don't have to really analyze what is the behavior of the system you're trying to model. You don't need to say what depends on what, in which way, okay? And this is where it makes a difference. So sometimes it can take a substantial amount of time to configure your BDLM model because you need to have an understanding of what's going on, which is not the case with LSTM. You can directly just crunch the data. The LSTM is going to figure out what are the dependencies. If you want to have all the details regarding this case study, you can go look at this reference that was done in collaboration with my team. So Barkop Deka, Dai Von Van Dang Wong, myself, and 2 engineers from Hydro-Quebec. So in summary for the LSTM, so the key part is the cell state. The cell state is going to be the long-term memory on which we can depend on. We have also the hidden states that are going to be used in the same way that hidden states are used in a traditional neural network. And in order to operate on the cell state, we need a forget gate, which is a vector of the same size as the cell state, which contain values between 0 and 1. The zeros are going to erase from the past memory, the 1 are going to keep. So again, it's not strictly 0 or 1, it can be anything between 0 and 1. The input gate is going to say, where do we want to write new information in our cell state? C tilde is going to be our candidate values, which can be between -1 and 1. And our new updated cell state is going to be the element-wise product of our forget gate times the previous cell state, plus the input gates, multiply element by element, again, the same typo, by C tilde. So the candidate values at time t that we computed here. So the t-1 shouldn't be there. And finally, our new updated hidden states are obtained by looking at which values from the cell states are relevant right now. So we're doing this by multiplying our output gauge, which contain values between 0 and 1 and has the same size as our cell state, with the 10H transformation of the cell state. Okay, so that's going to be strictly between -1 and 1. And what is it going to do? It's going to bring attention only on the relevant subset of cell state that contain our long-term memory for what's relevant in the past for predicting either what is now or what we're going to see in the future.